Hi, my name is Ashlyn Whitfield, and this is my video report on my Physics 2211 Lab Experiment 1. What's the purpose of this lab? Why are we doing it? In terms of physics principles, we're doing this lab to compare the predicted motion of an object with constant velocity to the observed motion of the same object. And in terms of skill building, we are doing this lab to learn to use tracker and glow script to complete analysis in physics class. Our initial conditions. Our system is equal to our soccer ball. Our surroundings are our wooden platform, the air, my hand, and everything that isn't the soccer ball. The initial time is 0 seconds, the final time is 2.4 seconds, the initial position is 0 meters, the final position is 1.77 meters, and the velocity is 0.75322 meters per second, which was found by dividing the displacement by the time period and used for our computational model input for velocity. The net force is equal to 0, which was an assumption made when establishing constant velocity. And this means that there is negligible rolling friction, air resistance, and other various forces. Models and principles. I'll provide a brief overview of my computational model. It was based on a set of starter code with a few modifications, including delta t equals 0.1 seconds instead of 0.01 seconds. This change was made in order to align with the data points collected via observation and simplify analysis. For our while loop, I set my t less than 2.45 seconds, which is the length of a video, plus a little wiggle room. For the fnet, we set the vector to 0, 0, 0, because we established that the net force is 0 newtons. For the ball.vel, we established the vector 0.75322, because the 0.75322 meters per second is the constant velocity of the ball. For the position of the ball, we included the initial position plus the velocity vector for 0.1 seconds, which is our delta t. More models and principles, this time for physics. The first physics principle that we address in this lab is Newton's first law. An object in motion will stay in motion unless acted upon by an outside force. Because we assume that Fnet equals 0, we assume that the ball will retain a constant velocity. The second principle that we apply is Newton's second law. The net force equals the mass times acceleration. We can approach our first statement backwards by assuming that because the ball maintains a constant velocity, acceleration equals 0 meters per second squared, and Fnet equals ma. Thus, Fnet equals m times 0 meters per second squared. Thus, Fnet equals 0 newtons. Thus, there is no outside force acting on the ball, which is what allows it to maintain the constant velocity. Here are our results. You can see a graph of the modeled versus observed motion of the soccer ball along with the corresponding data table. Here are our continued results, this time from the computational model, our constant modeled velocity, and the corresponding linear increase in position. Results explanation. We can see that both lines have similar slopes. However, the observed or actual position is slightly less than the model position for a portion of the graph or time interval. We can assume that this is because of the reality of a non-zero net force on the ball opposing its motion, such as rolling friction or the push from the hand. But we can also see that both the observed and model positions are 1.77 meters, or around there. Thus, we can assume that the forces acting on the ball are negligible in the context of the total time interval, initial time to final time, or T0 to TF. Finally, possible sources of error that may affect these conclusions. One such is imperfect tracking. The center of mass of the ball was hand-tracked frame by frame, resulting in position discrepancies due to human error. What if? What does it mean? These are important questions for understanding this lab. The first question we'll address is, what if my axes were flipped? If my axes were flipped, all my positions would have the same magnitude, just negative. And as time will always continue linearly in the positive direction, the velocity would be affected in the same way as the positions, negative with the same magnitude. Thus, they would have the same speed, but not the same velocity, as velocity includes direction. The y-axis doesn't matter for this lab, as we are only analyzing the x component of velocity. Second question, is it possible for me to say how many pushes and/or pulls added up to 0 in my observations? No, because we don't know what's going on in our surroundings. We know that there is rolling friction opposing motion, but we don't know if there is wind pushing the ball or how much drag is affecting the ball. There could be battling leaf blowers off screen fighting to push the ball. There's literally no way to know. We simply assume ideal conditions based off of our observations and in order to model our motion simply.